All right, today I will be talking about an analog of topological dimension and how it gets distorted or preserved under various maps in the plane. And this is joint work with my advisor, Jeremy Tyson. There are various analogs of topological dimension. Intuitively speaking, topological dimension asks us, if we have a microscope, how does a space look when we go really close to the space? For instance, this set of integers, under a microscope, they look like points to us, so the space is zero-dimensional. However, what if we move really far away under a telescope? How does this space look to us? It looks like a line. It is one-dimensional. And that is the asymptotic, that is the large-scale analog of topological dimension, also called asymptotic dimension. And Assouad-Nagata dimension, also called as Nagata dimension, is an all-scale analog of topological dimension, meaning now we have a microscope, a telescope, everything in between, and what is the largest dimension we see in this process of zooming in and zooming out. For instance, for this set of integers, the largest dimension we see in this process is 1. And in order to define, so today's talk is going to be about Assouad-Nagata dimension, this all-scale invariant of all-scale analog of topological dimension. And in order to define Nagata dimension, we need to understand two properties of a cover. The first property of a cover is S-boundedness. Fix a positive real number. A cover of a metric space X is S-bounded if diameter of each element of the cover is at most S. Second property is S multiplicity of the cover, which measures how much overlap exists between the elements of our cover. For instance, it is more precisely, it is the maximum number of elements any S ball, a ball of radius S around a point, intersects the elements of the cover. For instance, for real line, if I cover this real line by intervals of radius 2s, this is a 4s bounded cover. And the S multiplicity, if you take any S ball, these small red balls are the S balls. They intersect at most 2 elements of the cover. So S multiplicity is 2. Now we are ready to define Assouad-Nagata dimension, which is Assouad-Nagata dimension for a metric space is at most n. If there exists a global constant, this is the constant which will be used for bounding the diameter, such that for any scale, any positive real number, there exists a cover, our space admits a cover which is CS bounded, and S multiplicity is at most n plus 1. The Nagata dimension is 1 less, and minimum such n is precisely the dimension of the space. Going back to the example of real line, for instance, we found a 4S bounded cover with S multiplicity 2. So Assouad-Nagata dimension is at most 1 for this space. This is the upper bound it is generally a hard, this is a hard part to evaluate the lower bound as well. But for real line, Assouad-Nagata dimension is 1 as well. Now, about mappings and dimension. So how a dimension is distorted under various maps has been an essential tool in various fields of mathematics. For instance, homeomorphic invariance of topological dimension is used in low-dimensional topology, manifold theory, and many other fields. Quasi-isometry invariance of asymptotic dimension, the large-scale analog, is an essential tool in geometric group theory to study boundaries and some similarities of groups. Similarly, a key result about invariance of Nagata dimension was given by Urslang and Thiele-Schleichen-Meyer. They proved that Nagata dimension is invariant under quasi-symmetric homeomorphisms. These maps are homeomorphisms, but they preserve some more geometric properties. For instance, they distort the relative ratio of distances of 3 points in a controlled manner. So, however, these maps take bounded sets to bounded sets, unbounded sets to unbounded sets. And we just saw that Nagata dimension is an all-scale invariant, all-scale dimension. It sees every scale. So really the story is incomplete. There might be some more maps which preserve the dimension. Maybe some maps which take bounded sets to unbounded sets. And this was precisely work by Xiandong Xie, where he proves that quasi-Mobius maps also preserve Nagata dimension. These are the maps which are composition of quasi-symmetry and inversions. Inversions invert the boundedness, right? If you have an unbounded set under metric inversion, you go to a bounded set and vice versa. And it is actually a bigger class of quasi-symmetric maps. And so our goal is, can we broaden this class even further? Are there more geometric maps which preserve Nagata dimension? What about something called quasi-conformal maps or quasi-regular maps? Quasi-regular maps are not even homeomorphisms now. Well, just to give you an intuitive definition of quasi-regular maps are geometric maps which take really small balls to small ellipsoids, meaning infinitesimal balls go to infinitesimal ellipsoids of bounded eccentricity, and there is some constant, like k quasi-regular means that distortion of eccentricity is k. And quasi-conformal maps are nothing but quasi-regular maps which are homeomorphisms. That is, yeah. And few examples of such maps are in plane, they are holomorphic maps are quasi-regular maps, and conformal maps, which are also homeomorphisms, are quasi-conformal maps. Every quasi-conformal map is a quasi-regular map, and thus conformal maps are also quasi-regular maps. So then, in order to study this question, we move first to the two-dimensional case. We want to study these maps in 2 dimensions. And we prove that for a quasi-regular map, if the subset is a compact subset of our domain, then Nagata dimension is preserved. And in order to, so an obvious question is this the best that we can do? Do we really require the compactness of the set? Well, the answer is yes, because consider e to the z, it's a conformal map, so it's quasi-conformal. It's quasi-conformal, so it's quasi-regular. This distorts the dimension of natural numbers. It's a subset of C. So really, we cannot, in full generality, quasi-regular or quasi-conformal maps cannot preserve Nagata dimension. However, there are certain maps, quasi-regular maps that we will see, which preserve Nagata dimension for any subset of C as well. And the key ingredients of the proof lies in this Stoilos factorization. In planar case, we can write any quasi-regular map as composition of a quasi-conformal map and an analytic map. So really what we want to prove is 2 things. One, that quasi-conformal maps preserve Nagata dimension of a compact subset. And second thing is analytic functions or analytic maps also preserve Nagata dimension of a compact subset. Now, for quasi-conformal maps, the proof is a bit easier because they are locally quasi-symmetry, and by result by Langen-Schleichen-Meyer, we can have a finite subcover of the space, and on each element of the cover, Nagata dimension will be preserved because it is quasi-symmetry there. And however, for analytic maps, we use this property that any analytic map around a critical point can be written as composition of conformal maps and a polynomial, a monomial. And really, the point boils down to proving whether polynomials preserve Nagata dimension or not. We consider general polynomials, and we prove that, first we prove a proposition that for any polynomial, we can divide the entire complex plane into finitely many pieces. They might not be as nice as shown here for monomials, but on every such piece, on every finite piece, your map will be quasi-symmetric. And quasi-symmetries preserve Nagata dimension. So for each piece, Nagata dimension will be preserved. Now there's, again, in the paper by Langen-Schleichen-Meyer, they also prove that Nagata dimension is stable undertaking unions, finite unions. So Nagata dimension of each piece is preserved, which is why Nagata dimension of the entire complex plane is preserved. And thus, we obtain, by using propositions, stability, quasi-symmetry results, we obtain that for a non-constant polynomial, Nagata dimension is preserved for any subset of complex plane. And then we use Xiandong-Xie's result on inversion, and this proposition also implies that for non-constant rational functions, also preserve Nagata dimension of any subset of complex plane. So this is the story for the planar case, and then we also then now we are working on generalizing this to higher dimensions, and there are various questions one can also ask in two-dimensional case. What about other analytic maps? We have results like for a very large class of analytic maps, Nagata dimension, there exists a subset for Nagata, for which Nagata dimension will be indeed distorted if it's an unbounded set. And yeah, so this is the, this is my talk. Thank you.